Hey everyone, welcome back. This is the fourth session of AP Chem, and I wanted to go over a little bit of housekeeping before we get started on Unit 1 review. On April 1st, you're able to go to the school site and rent out a Chromebook. So if you're just working on your cell phone and that's all you have at home, I highly suggest going and get a Chromebook. That's going to help out. And in case anything comes up where you need to type or view PDFs and your screen's just too small on your phone. So absolutely take advantage of that. They have plenty of Chromebooks for everyone. By April 15th, which I think is a Wednesday of that week, we're going to be able to start Classroom up again as far as assigning new assignments and starting up our grades again. So that's tentative right now. I'm going to get more information on Friday about a couple things, but yeah, mid-April we're going to start class up again as far as grades go and assignments. For us, that's primarily going to be through Google Classroom. That's worked the best, and you can access that through your portal. So I'll be uploading assignments through Google Classroom. Make sure you have your notifications on. You'll also see the assignment categories pop up in Q as I assign them. I'm going to keep on that. So you can look at Q for the instructions. I'll upload the documents to Q and Google Classroom when I do that. And of course, if you have any problems moving forward with that, you can let me know. But yeah, mid-April, we'll start that up again. So we have a couple weeks before that starts. And then get your Chromebooks on April 1st. And then this Friday, April 3rd, I will be getting more information about the AP test as far as when those dates are going. So I'm excited for that. We'll be able to figure out what our timeline's looking like moving forward and be able to plan. So that's it for the housekeeping. Let's go ahead and jump into what we're doing today. All right. I have a series of questions that we're going to go over for Unit 1, Part 1. Unit 1 focuses on atomic theory and the periodic table, and that includes moles and molar mass and electron configuration and things like that. So as I go through here, I'll be dictating and putting some responses up here. A full typed out response will be provided online through Google Classroom afterwards. So here we go. I wanted us to be able to use concepts of molar mass and the idea of molecular weight for differentiating number of particles. So if we have an equal mass sample, then we have to think, how does carbon, water, and sodium chloride differ if it's all three samples are the same mass? And so our goal is to figure out which has the greatest number of particles. And one of our resources that we have to connect number of particles to grams is Avogadro's number, and that is connected through the idea of the mole. The mole is in the middle, and 1 mole is the 6.02 times 10 to the 23rd particles. And 1 mole also equals some sort of mass per the substance. So for carbon, it's going to be that 12.1 carbon in a 20 gram sample because it weighs less. And then sodium chloride weighs a lot, so it's going to have fewer particles in a 20 gram sample. If you want to think of it another way, if you have a 20 gram sample, then 12 of that is just carbon. So we're going to have more than a mole. We're going to have somewhere between 1 and 2 moles of carbon. But if you have that same 20 gram sample for sodium chloride, then it's going to be way up here, 58 grams per mole. So we're going to have significantly less than 1 mole of sodium chloride. So the answer to this one's going to be carbon, because the most number of particles should have the smallest molar mass when we're making a comparison like this. And if you want to do the math for it, you can go ahead and calculate moles and convert that to particles, and you can see that carbon's more than a mole and sodium chloride is significantly less than 1 mole. And water is somewhere in the middle. The part about justifying this would have to be making some connection to the logic you're using, which in this case is using the idea of molar mass, which we got from the periodic table. Now, the AP test is going to be more focused on free response. There's actually, from what I heard recently, there's going to be 0 multiple choice to minimize cheating, and it's going to be all some sort of written response that you're going to be submitting. So they're definitely changing the format than what we're used to. That doesn't mean we're not going to look at some multiple choice questions to help us review concepts, but understanding concepts and being able to justify and explain what we're doing is going to be much more important moving forward. Okay, so that was the first question to get us started, looking at molar mass. The next example I had, if I can, there we go. I wanted to bring back ideas of isotopes, what an isotope is, and how isotope mass compares to average atomic mass. How does it compare and contrast? So isotope mass is sometimes referred as just the atomic mass, but it's isotopes about one atom at a time, one isotope, singular, where average atomic mass takes into account trillions and trillions and trillions of atoms. Isotope is singular, one atom at a time, where so you can have a carbon 12 isotope, you can have a carbon 13 isotope, carbon 14 isotope, where the masses are different, 12, 13, and 14, but they're all carbon. So they all have 6 protons. They all have 6 protons. The only difference between them now is the number of neutrons, where we have 6 neutrons versus 7 neutrons versus 8 neutrons. And so with carbon, reactivity-wise, all isotopes are going to react the same. Reactivity is based on protons and electrons, which is that electrostatic force between atoms. The number of neutrons actually doesn't change the reactivity at all. So it doesn't matter if it's carbon 12, 13, or 14 as far as how it's going to react. It just changes the weight a little bit. And what we see is that the vast majority of the types of carbon in nature is carbon 12. About 99% is carbon 12. And then for 13 and 14, it's less than 1%. 13 being a little bit more than 14. 14 is like 0.0001%. So it's really, really small. Very, very small. And this is still like less than 1%. So the majority of it's carbon. What we're using these isotopes for is we're taking this, or we can use this isotope and the percent abundance, how often it occurs in nature. So we take any given sample of carbon, pure carbon. We're going to say about 99% of it's going to be carbon 12, and then the other 1% or less is going to be these heavier isotopes, 13 and 14. We're going to take the percent abundance and their mass numbers. This 14 is more appropriately called a mass number, which is just protons plus neutrons. Percent abundance with their mass number, and we combine those to get an average atomic mass. An average atomic mass is an average of all isotopes based on the percent abundance. So to get this average mass, mathematically, we're going to take this 99% as a decimal and multiply it by 12, which is the mass number there. And we're going to add it to the 1% times the mass number 13 plus the significantly smaller percentage for isotope 14. If we add all these together, we're going to get this average mass, which for carbon is about 12.01. And that's going to be units of grams per mole, as we'll see later. Average mass, average atomic mass, and molar mass are the same thing. And that's kind of a misconception early on, is why we're using average mass and this idea of molar mass. Well, average atomic mass is used early on when you don't really know what the mole is. But for us, we were incorporating ideas of moles early on. So we were just mainly using molar mass. But just to clarify, molar mass and average atomic mass have the same numeric value. It's just molar mass brings in the idea of that's how many grams are in 1 mole instead of some average atomic mass units. Average atomic mass is sometimes presented as atomic mass units, which are just some units that are mainly used, are only really used on the atomic level. And the idea is if pure carbon-12 is 12 atomic mass units, 12.000, exactly 12, then we're basing all the other isotopes and mass values off of this. And so this is where the mass value comes from, is pure carbon-12 weighs 12 AMU, and pure carbon-12 is 12 grams per mole. So the foundation of this mass value, this molar mass value, the average atomic mass value, is based on carbon-12, that isotope in particular. And that's some fundamental knowledge about mass and atomic mass that's going to be helpful. Just where does it come from? What's our unit of measurement? That's where's our standard. Like the temperature scale for Celsius is based off of water. The atomic mass units and molar mass is based off the isotope carbon-12. Which goes beyond what this question was asking, but I know you guys were curious, so I brought it up anyway. How are we doing? Questions so far? Pause for comments. I think we're good, pretty straightforward, good review of early stuff we learned. And of course, I skip a question, or if I skip what your question was, or if you had a question that you thought of later, you can just write it down and just email it to me or ask me at the end. So I brought up the example for iron. Iron has 4 stable isotopes, and none of which are iron 55. So with this information and the periodic table available to us, what would be the most abundant isotope of iron? And we need to justify that. So what I'm going to do is I'm going to look up the molar mass of iron. So I'm going to go to ptable.com. And the molar mass of iron, when you look at the tile for iron, we have the atomic number here, and it says 55.845. And as far as the most abundant, if this 55.845 is the molar mass or the average of all isotopes, then what we can do to predict the most abundant one is just round this up to the nearest whole number. So if we round that up to 56, we can say that iron 56 is most likely the most abundant isotope that occurs in nature because it's the closest one to this average value. When in fact, if you look up iron, 54, 56, 57, and 58 are common isotopes of iron. But we don't really even need to know that. We would just need to round this number to the closest integer and say that that isotope of iron is the most abundant. As far as the justification goes, we would just need to make sure to reference the molar mass from the periodic table and mention that by rounding that to the nearest whole number, we can be able to predict the most abundant isotope. Okay. Moving on. This often shows up as a multiple choice type question every once in a while, but what makes it more of an AP level question that we might see on the AP test is just this justify element. How do you know that the answer is correct? Where are you getting information? Is it legit that we're able to round to the nearest whole number? And it usually works. All right, speeding through the first few questions. Here we are on the 4th question that I brought up for today. Mass spectroscopy. Mass spectroscopy is a graph based on intensity of this mass value, or sometimes this is mass value. This one in particular said times per minute. That usually this would be a mass. Sometimes when I pull these graphs, these examples off the internet, they're not labeled the way that we would see them on an AP test. Let's just assume that that's a mass value, like a molar mass value. And let me scroll up. Get rid of this because I messed that up. Let's assume this is referencing a mass. So what we can do is look at each of these peaks and predict kind of what that peak represents. This middle one is somewhere in between 20 and 25. So we'll say about 23, 22 and a half. And this one's pretty much 25. And then we have one that's over 25. And the question says, predict the average atomic mass of the element if these are the three isotopes. Each of these peaks represents an isotope. So I could say that this one is 20, maybe like 22 point, closer to 22, not exactly 0.5, so maybe 0.3. And this one we can just say is about 25, and we can say that this one's about 27. So the intensity is relative to percent abundance. Intensity and percent abundance are very closely related. Intensity is just a word used for a machine as far as how often that that particular particle is registered on the machine. That's the intensity. So the one that's between 22 and 23 shows up the most. So we can say that's the most abundant. And because that's the most abundant, like we did on the previous examples, we can say the average atomic mass is going to be the closest to that one. Now I can't just say 22, it's going to be somewhere greater than 22 because we have some isotopes that are higher than that. So I'm going to say about 24, somewhere around 24, maybe 25. And then as far as predicting what element this could be, I'm going to take that number, that 24, 25. So my prediction is going to be somewhere out there. So predicted average, just to give a location on the graph where I'm predicting. So I'll go to the periodic table and I see that that's about magnesium. Magnesium has an average mass just around 24, specifically 24.305. And that's really the only one that's the closest to what we're seeing on the graph. So I would say that's a reasonable prediction. And we did a bit of this. You're not going to have to do this for compounds. One of the redactions on the AP test is that we're only going to use mass spec graphs for elements, not compounds, which is nice. Simplifies it a little bit. Okay, so we can use this graph to talk about intensity, which one's the most common, most abundant isotope, and then we can use that information to predict what element is being represented by the graph. There was a little bit in Unit 1 about differentiating between compounds or composition. So we had mixtures, we had compounds. Within the mixtures category, we had homogeneous and heterogeneous. And then a compound is a type of a pure substance. And there's all these there's this flow chart that we looked at for this unit to show all the separations between compounds. So the big difference between mixtures and compounds is mixtures can be separated by physical means, and compounds can be separated only by chemical means. So I want to identify what physical means are and what chemical means are, what kind of options we have in the lab, what kind of reactions have we seen that represent chemical means, what are some examples of these physical versus chemical. But knowing that mixtures can be separated by physical means and compounds can be separated by chemical means is one of the big ways to differentiate between a mixture and a pure substance like a compound. So a mixture. Let's take an example of a mixture. A mixture is anything where you have a container, more than one type of substance is put together in there. So usually we're thinking of like water with table salt, and if it dissolves, then we call this a solution, and that's a type of a homogeneous mixture. If we have something that doesn't dissolve, like we take oil, it's still two things in the same container. And so it's based on what's inside a container. Two things in the same container, that container has a mixture in it. And the oil and the water are not going to dissolve because water is polar, oil is nonpolar, so they're not going to correspond or coordinate with each other. And so we're going to get these two layers. It's another word for not dissolving when you have two liquids is immiscible. So if two liquids dissolve in each other, it's miscible. When two liquids do not dissolve in each other, it's immiscible. So oil is immiscible in water. And so we're going to see these two different layers. The one that is less dense will stay on top, and the more dense one will be on bottom. So these layers will be separated by density. Now, how do we separate these things? We have oil and water where we're separated by density. And then to bring up our other example, we had a dissolved salt solution where this is just salt water. And when something's dissolved in water, we say aqueous. So how are we going to separate these? Because these are both some mixtures. One's heterogeneous, one is a homogeneous solution. Well, the oil and water, you can actually separate using a pipette. You can actually just take a little dropper, stick it on the top, and suck out the oil and separate it. It's not as perfect because you're going to have a little bit of oil, but it's a very valid way of separation, at least to get the large amount of oil out of there. And then you can let it resettle, and because it's separating by density, you'll definitely have this top layer of oil remaining, if anything is remaining. Another way I'm going to do physical means, right? Physical, you can use a pipette. Now, it might be a little trickier with the oil, but we can use boiling point to separate two liquids. And this is called distillation. Distillation is separated by boiling point. Now, if you cook with oil, it takes a lot to boil off the oil, or to get the oil to vaporize. So distillation may not be the most effective with oil and water, just the pulling it away, because you can already see the two phases separating. Pipetting for the oil and water will be effective, but if you have two liquids that dissolve in each other and make some sort of salt solution, you can boil off the water. So for salt water, you can evaporate out the water, and the solid salt will remain. And then we'll talk about distillation a little bit more. If the salt, let's say we take a salt that's insoluble, so I'm going to get rid of this aqueous word, and we're going to bring up an example of an insoluble salt. An insoluble salt, that's where you get some sediment at the bottom. And a way to get this solid out of some liquid would be filtration. So right now we're looking at examples of physical means of separating mixtures. A mixture is comprised of two or more substances. Now, as far as compounds go, an example of a compound is going to be water, carbon dioxide, hydrogen peroxide, some sort of compound that has a chemical formula. There's multiple atoms forming one individual molecule in this case. So in the idea of hydrogen peroxide, how can we break this down further? Well, we have to use some sort of chemical means. And we know that hydrogen peroxide, to use this example, goes through a decomposition reaction, which can be further catalyzed by iodine, the iodide ion from potassium iodide. This is the elephant toothpaste. But with a catalyst, we can cause this hydrogen peroxide to break down even further, or even faster. And just to do a little balancing, there we go. So this would be a chemical reaction. This would be a decomposition process. So essentially the names of chemical reactions are going to be the chemical means. Sometimes if you have hydrogen peroxide, hydrogen peroxide is stored in those brown bottles to prevent UV light from coming in. So UV light could also be a catalyst or help provide excess energy to cause this decomposition to happen faster. We can use the iodide catalyst, but the chemical means there is just a decomposition reaction where chemically, how are we breaking this down into smaller pieces? So compounds can be broken down further. As far as the water molecule, How are we going to break this into individual elements or break this into their elemental form? We can apply energy, and this is called electrolysis. We can actually break the water molecule down into its elemental components, hydrogen and oxygen gases. And we see this with an electrolysis process. You just apply electricity, and you're going to have some salt in the water to get the current to flow through the water molecules, but by applying energy in the form of electricity or put a current through the water molecules, you actually get it to separate into its elemental form. So those are examples of chemical means, just breaking down a compound into smaller pieces. So back to our original question again, mixtures and compounds. The question I ask when you're trying to differentiate between these is, how can you separate it into a smaller piece? If it's physically separated, you can use physical means to separate it, then you know you have a mixture. If you have to use chemical means only to separate it, then you know you have a compound. Distillation is an interesting technique, and it does require some expensive glassware. And so we'll be just discussing the concept of distillation. If we have two liquids that dissolve, so we're going to have to take something that is polar, a liquid that's polar, like an alcohol. So let's just take ethanol. Ethanol and water. They both have hydrogen bonding, and so they're both going to be polar molecules, and so the ethanol will dissolve in the water. The difference between ethanol and water is they have different boiling points. And so as you increase the temperature slowly, we're going to see the one with the lower boiling point leaves first. And you'd be given these boiling points. You wouldn't have to remember which one. And basically the one with the lower boiling point is going to evaporate first, get into this tube, which is called a condenser, and it's going to separate out and leave the remaining solution. The one with the higher boiling point is going to remain. The one with the lower boiling point is going to be separated out. So what kind of samples would this work for? 2 or more liquids that have different boiling points. Filtration does not work for 2 different liquids. They're both going to just fall right through the filter paper. You'd have to have some sort of insoluble salt, which is also sometimes referred to as a precipitate or sediment. All these different science words for the same thing. Then you'd use just filter paper. Okay. Number 7. We used photon electron spectroscopy, or otherwise known as PES. Photoelectron spectroscopy. And this is a reading that gives indicators of what energy levels are detected for a sample. And again, we're not really going to be using compounds for this. We're only going to be looking at elements, pure elements, and which allows us to make some predictions using the periodic table and what we understand about electron configuration and how electrons are arranged in energy levels and orbital shapes. Just a quick review of the orbital shape. We've got s orbitals, we have p orbitals, we have d orbitals, and f-shaped orbitals. We're really not going to have to talk about the f-shaped orbital too much as far as the electron configuration. What you should know about the f orbital is just how many orbital types there are, or how many different shapes there are. There's 1 s-type orbital. There's 3 different p-shaped orbitals. There's 5 different d-shaped orbitals, and there's 7 f-shaped orbitals. And each of these orbitals holds a maximum of 2 electrons. So there's a total of 2 electrons that can fit in all of the s orbitals on any given energy level. And on any given energy level, there can be 6 electrons in p orbitals, 10 electrons in d orbitals, and 14 electrons in f-shaped orbitals. And that's on any given energy level. So if we go to the periodic table and we're looking at row 6 or period 6 all the way across, there's going to be s, p, d, and f-shaped orbitals. And these are going to be the maximum for that energy level in particular, that 6th energy level. And these numbers reset when you go to the 7th energy level. You get new S-shaped orbitals on the 7th energy level, and so on. We can do a deeper dive on electron configuration on a separate video. But we're going to be using this idea to help connect to this graph. So I'm going to get rid of the ones that aren't as relevant. We're not going to see d orbitals on photoelectron spectroscopy graphs, the PEF's graph, and we're not going to see f orbitals on these graphs. We'll mainly be seeing s and p orbitals. So how does this relate to ionization energy? If we know that relative number of electrons talks about these electrons that are in s orbitals and p orbitals, we used to use the Bohr model for the first energy level, second energy level. We said the max of 2, then the max of 8. And then the Bohr model is not very accurate past hydrogen. So we're using more an energy diagram of the first energy level with s orbitals, second energy level with s orbitals, then the second energy level with the 3 different types of p orbitals. And then we can go to the third energy level with s orbitals. We use this more of this energy diagram this way to represent where electrons are most likely to be. So if the nucleus is down here at the bottom of this graph I'm drawing, and as we move up, we're getting progressively further and further away from the nucleus. So we're going to say this is distance. So the further you away from the nucleus, if I can draw kind of some circles to represent these energy levels, kind of like the Bohr model we'd see, the further away the electrons are from the nucleus, the less of a pull it feels by that nucleus. So in terms of binding energy, the ones that are the closest to the nucleus should have the greater binding energy, because it's going to feel the nuclear pull more. And binding energy is a direct relationship to ionization energy. Ionization energy is the energy required for an electron to be removed. So when we look at this graph, we see that the highest numbers are on the left. So those should be for the electrons that are the closest to the nucleus. These should be 1s electrons because they're the closest to the nucleus. And if we look at relative number of electrons, we know that the 1s is going to fill up first. So this height right here should represent 2 electrons. And then the next one in order is going to be 2s. So these are 2s electrons. And then the higher peak should represent 2p electrons. And we're not going to have a peak after that unless the 2p block is full. So we know that this is going to be 6 electrons right here. Once 2p is full, we're going to go over to 2 electrons in the 3s orbital. And we know that's 2 because it's about the same height as the other ones. Now, this is assuming ground state conditions. Ground state conditions means there's no excited electrons jumping around. They're all in order of 1s, then 2s, then 2p, then 3s. And in fact, we use exponents to represent how many total electrons are in those particular orbital types. And if we add up all these exponents I just wrote, 2, 2, 6, and 2, we get 12 electrons. So whatever this element is, it has 12 electrons. And so if we assume it's a neutral ground state element, we're going to say that this is magnesium. Magnesium. Questions on that? Because now we're getting into a little bit more complicated stuff. the left of the graph where I said is the 1s orbital, just be careful and read the numbers on the axes, because sometimes they'll flip this graph, and so the left will have 0 and the right will have the highest numbers, but I don't see that as often. Usually the graph goes from left to right in order of the 1s, 2s, 2p, 3s, in order of the electron configuration. So it's a pretty safe bet to just start on the left and say that's your 1s, then the next one is a 2s, and then moving on from there. So just to review, how does ionization energy relate to determining the electron configuration? We can say the ones with the highest ionization energy or binding energy should be the ones that are the closest to the nucleus, which is the 1s orbital. And then as we move on and fill up our orbitals, we can say the one with the lowest binding energy are the valence electrons for magnesium, which has 2, and those are the ones that are the furthest away from the nucleus. So again, they have the lowest ionization energy. Okay, this brings us to our last question. I kind of answered this on the previous one. It says, predict what element is shown on the graph. And I said, well, if this has 1s2, 2s2, 2p6, 3s2, that in order is going to be the full electron configuration. And this matches magnesium in the neutral ground state. Sketch a new diagram for the most common ionized form of this element. What key adjustments must be made? And I'm looking for 2 specific ones. So what I'm going to do is I'm going to pause the video really quick. I'm going to give you a chance to think about this, and we can have a quick discussion, and then I'll go ahead and start the video again with our answer. All right, we took a brief intermission, and now we're back. We're going to finish up this question. When we're looking at the ionization of magnesium, metals are going to lose electrons. When we look at this outer energy level, the 3s2 electrons, this means there's 2 electrons in the outermost energy level. They're the furthest away from the nucleus. There's in fact a shielding effect on these outer electrons. The 1s electrons are the closest to the nucleus, and when it's a full shell, it shields the remaining electrons, which allows them to be a little further from the nucleus. And then the complete 2 energy level, this complete second energy level, is going to help shield the electrons on the 3rd energy level. The 3rd energy level electrons are the furthest from the nucleus. So when we're looking at ionization, the furthest from the nucleus has the lowest ionization energy, and these ones are going to be able to leave. So when we look at the ionized form of magnesium, it's only 1s2, 2s2, and 2p6. So that is the adjusted electron configuration of ionized magnesium. And you'll notice that it has a noble gas electron configuration similar to neon, neutral neon. So what I'm going to do first is I'm going to redraw these 3 remaining peaks as close to where they appeared before. So we had one in between 127, 125. There's an equal height peak on 9. And then about a little less, a little greater than 5, we're going to have that 2p peak. And so this is what we could predict happens when you just lose the outermost electrons. But there's something else that happens here. What happens is now that there is fewer electrons, let me get rid of some of this over here. Now that there's fewer electrons, and this is where I kind of like using the Bohr model a little bit, we have this plus 12 nucleus in the center. And then we're going to have 2 remaining energy levels, the first one and the second one. And we have got 1s electrons here, and we have 2s and 2p electrons on that second energy level. And that 3rd energy level is no longer being occupied. Normally when those electrons were there, let's put those 2 valence electrons, they're still feeling the pull from the nucleus. And the plus 12 charge is separated between 12 electrons equally. And what happens when we get rid of these valence electrons and they go away is now all these other electrons are feeling that plus 12 pull, and that plus 12 pull is split between only 10 electrons. To do a little math, before it was a 12 electron to 12 proton ratio. Actually, it makes a little more sense to keep the protons on top mathematically. 12 proton to electron ratio. And that was a ratio of 1 to 1, equal share between all the electrons. In the ionized form, we have 12 protons per only 10 electrons. So you can see each of the electrons get about a 1.2 pull per one. So there's a greater proton force per greater positive force per all the electrons. And it actually pulls the energy levels in a little bit more, decreasing the radius. This is called the ionic radius. Positive charge particles get smaller than their neutral form. And now that they're smaller, we're actually getting these electrons closer to the nucleus. And what this does is it increases the ionization energy of every electron. Because all these electrons are getting close to the nucleus, what we do to be more accurate, and now we're still just estimating the approximate location of these curves because we don't know the exact numbers, but we're going to say that all of these remaining peaks are going to shift to the left, where they're all increasing in ionization energy. So this is the adjusted 1s, 2s, and 2p electrons. To all of them have higher ionization energy because the size of the atom gets smaller. All of the electrons are now closer to the nucleus, so they're all affected. So not only omitting that last peak is one adjustment that needs to be made, but we need to shift all of the peaks to the left so that all of the remaining electrons have a higher ionization energy. And this is actually why magnesium typically only ionizes twice. Those two outer electrons were those valence electrons, and those were here on the right side of the graph. Now that those are gone, any additional electron is going to be requiring a lot more energy. So under normal conditions, there's not going to be the available energy to get those extra electrons to remove. Only those two ones are going to be, those two outermost 3s electrons are going to be the standard ones to leave. So we just went through 8 questions as far as introductory review for Unit 1, which is mainly atomic theory. I do have a couple questions in chat that I want to address, and then we'll go ahead and just continue a Q&A after I stop the video. But I wanted to reiterate, why do they shift to the left? And as far as where exactly to shift these peaks, I'm making a prediction. And so I know there's numbers there, but where I'm shifting from a 5 to a 7, for example, this is just an estimation. So it is absolutely okay to make an approximation of where they're going to be shifting to. If there's any additional information as far as what the new ionization energies are, absolutely try and get as accurate as possible. But just showing a generic shift to the left of all the peaks should be sufficient as far as a prediction model or just a sketch. They are shifting specifically to the left because if we look at all the numbers on the bottom, that is the ionization energy. And when the atom's getting smaller, we know that all of the electrons are going to have an increased ionization energy. When an electron moves closer to the nucleus, then it's going to take more energy to remove that remaining electron. And that's an increase in ionization energy. And because those numbers get larger to the left, we're going to shift to the left towards those large numbers. If we were ionizing and gaining electrons and the atom was getting larger, then it could be potential that we're going to be shifting the other direction. But usually with these graphs, we're really only looking at ionization energy as far as removing electrons. I haven't seen too much as far as getting to our anions where we're gaining electrons. What's the shift? Okay. I threw out a word called binding energy. Binding energy and ionization energy represent pretty much the same thing. Binding energy is the energy required to remove the electron. And then that corresponds to ionization energy. Now, if we're looking at delta H's, like for this process, where if we're getting a little back into thermodynamics, let me clear this up. A little bit of an extension. We can write this as a chemical equation where the first ionization energy, and then we take that ion and get the second ionization energy. Each of these have a different energy value. Once you remove the first electron, the second electron actually costs a little bit more energy. And these could have delta H values as far as enthalpy values. What we can predict for the sign is we could say that this should be a positive delta H because it requires energy for the electron to leave. If we're going through the opposite process and gaining electrons, like when we see for oxygen, where it would gain an electron to get to the O minus, and then gain another electron to get to the O2 minus, we would predict that this would have a negative delta H because it is the opposite process where an electron is joining the atom, becoming more stable, and so that extra energy is released. So this is a way of showing the ionization as a chemical equation. And referencing the exothermic and endothermic process. Exothermic, releasing energy when the electrons join, and the opposite, endothermic, when the electron is being removed, or the energy is absorbed, allowing the electron to leave the atom completely. Good questions, I appreciate it. Other ones before we quit for today, as far as the video goes? Hopefully this question strategy helped. I want to keep bringing up these key questions to get us to review content in a way that we're formulating answers and justifying our responses. I think that's going to be really important moving forward. When we start doing assignments, I can ask you to prepare a written response first, and then we can correct it, and that'll be later in April. I just had a good question. Energy is released when, and so free oxygens, imagine one oxygen atom just floating around by itself. These are called radicals, free radicals. And they have their 6 valence electrons, and they're pretty unstable. Free radicals are pretty unstable. They're very reactive. And so everything really has this desire to gain a full electron configuration. It's just physics. And so there's empty space in the second energy level when that electron from some other source joins the oxygen atom, you get that charged particle, that negative charge. So that's a stabilizing effect because now the oxygen has a full set of valence electrons. It just so happens that that is a stabilizing effect. Atoms prefer to have a full octet. And that is the basis of most chemical bonding as far as covalent bonding goes or ionization. Muted myself for the comment. Good question. So yes, gaining electrons is a stabilizing effect. And so when that electron joins, excess energy is released. And it just so happens that is equal and opposite to the ionization energy. You're welcome. All right, I'm going to go and pause the video.